welcome to this video for the beginning of Chapter 4, Modeling with Geometry. To start this chapter, we're going to be looking closer at some common 3D shapes and how to find their volumes and work with their volume equations in order to find the missing pieces that are within those formulas. And then in later classes, like tomorrow, we will be looking at how we can adapt those to real-world situations and use shapes and geometry to solve problems as well. So with this first day, we're going to get into some volume of 3D shapes. We'll start off with prisms and pyramids as our first idea. So we have 5 questions as our do now. Most of these are pretty straightforward. So if you want to pause the video and think about how you'd answer each of these, take a second to do that now. Now with number 1, explain how the unit measurement square units relates to area. So when you think about square units, square should make you think of 2 or because of squared things. Area is only in 2 dimensions. So squared, 2 dimensions kind of equates and makes sense. Number 2 has how cubic units relates to volume. Cubes are cubic or cubed numbers, all relate to the number 3. Volume deals with 3 dimensions or 3-dimensional space, and that is why cubic units relates to volume. Number 3, the area of a square is 225 centimeters squared. What is the length of each side? The area of a square is represented by taking one of those sides and squaring it. So if I knew that my 225 centimeters squared area was the answer, if I square root both sides, that would tell me that the side length would be 15. And that would be how I get my answer. And just remember that centimeters squared doesn't mean you're taking like that number and squaring it after the fact. Centimeters squared, remember, is just square units. The volume of a cube is 64 centimeter cubed in number 4. So when you talk about the volume of a cube, that is just taking that one side that's all the same and cubing it. And if we know that's equal to 64, if we take the cube root of each side or figure out what number, multiply it by itself 3 times, well, that means that the side length would be 4. So lastly, number 5, the volume of a rectangular prism is 180 centimeters cubed. What might its dimensions be? So because we are dealing with a rectangle, we don't know that all the sides are the same like we do with squares. So that means they can be anything. So our volume here could be length, width, and height. So we just think you have 3 numbers that could multiply to 180. So that could be a lot of different things. Like we could do 20 times 3 is 60, and then multiplied by another 3 would be 180 centimeters cubed. And each of these would be centimeters, and that's why it ends up as centimeters cubed, because you have centimeters times centimeters times centimeters. And there could be lots of different other combinations of 3 numbers multiplying to 180. And if you include decimals, there's actually an unlimited amount of numbers that those could work for. So now we're going to get into our notes on prisms and pyramids more directly. So we have basically a square right here, and then we kind of have a big block made up of little squares. So if you were to think about, well, if I know the area of this square, like this could be a 1 by 1 square. Well, if it had 3 dimensions, like so, well, then if this was really a cube, it would be 1 by 1 by 1 for depth. So if you knew that this was the volume of 1 times 1 times 1, well, that just equals 1, or 1 unit cubed. And that means that if I knew how many of those little squares were on this whole thing, so I knew if I had 1, 2, 3, 4, 1, 2, 3, 4, 8 across the bottom, and 4 across the top, well, that means that I have 8 times 4 or 32 on this kind of front side. And then I have 4 of those, so 32 times 4 would be 132. And that's how you'd find the area, or the volume, I mean, of a prism, especially a rectangular prism such as this one. So the next idea is something we just kind of explored. Cavalieri was a famous mathematician in geometry, and he basically figured out that if you have two figures with the same height and the area of the cross sections at each height is the same, which in the volumes of the figures are the same, in simple terms, if we have this front playing card, well, the length and width of this first card is the same as every other card going backwards. So if you knew the area of one of these cards and you knew how many cards deep it was, you could take the area of the front card, multiply by how many cards you have going depth-wise, and you'd get the volume of that whole stack of cards or that whole rectangular prism, if that's what you were talking about. And then if you kind of look at the picture next to it, well, if they are all kind of out of order and kind of shuffled around, if you still have the same number of cards, no matter how they're oriented, it would remain the same volume. And all of those are part of Cavalieri's principle here. So now we have a rectangular prism. So if we kind of label these, rectangular prism is the name of that top left one. The top right one is a triangular prism. And the one at the bottom you might recognize is a pyramid. So as things before we talk about their volume formulas, so a rectangular prism is very familiar. You might recognize a pyramid as well. And first, the difference between a triangular prism and a pyramid is what are known as the faces. So if you look at the bottom of a pyramid, that bottom is either a square or a rectangle. That's what makes it a pyramid. And if you notice that we have a triangular prism where we have some rectangles on each face, but the ends are triangles. This right end right here, and then the end opposite it is also a triangle. And that's a big distinguishing feature of a triangular prism. And that's going to be related to how you find the volume of one of those triangular prisms. So that's different than a pyramid that has one kind of rectangular or square face, and then you have four triangles around kind of the top parts of that shape. Now, I will have the link you see here from GeoGebra to explore how the volumes relate to each other, especially for rectangular prisms and pyramids. So you can kind of use that link on my Google Classroom page or explore on your own. But kind of we'll move past that a little bit. So if we have a rectangular prism, we already know is length, width, and height. We already talked about that in an earlier slide. So if I compare that to a triangular prism, well, based on our numbers here, if you did this on a computer, well, you would see that 376.26 is about double 188.13. And so we have a triangular prism is always going to be half, as long as its height is the same, and as long as its rectangular base is the same as the two shapes. It will be divided by 2. But if you think about how this kind of is set up here in front of us, this triangular prism, so if your height is that for that back face, that line right there. So if you knew that you had a rectangular prism was length times width times height. Well, we don't have the same sort of stuff. So if we just look at the face here of our triangle, well, it would be 1/2 the base times the height for the triangular prism. So you have 1/2 times the width of it, and then the height would be the area of just the one triangle face, the one in the back there. And then you'd only need to multiply using Cavalieri's principle, kind of from J to I right here, this to know the depth. And so that would kind of be the length of it. So it's really the same thing as moving that half to the bottom. And so your volume of your triangular prism is really the same thing but just because of that triangle area idea, we would just be dividing it by 2. Now for pyramids, they're not half. This is actually 1/3, and that's something that you can explore on that GeoGebra link that I provided earlier, and you can find on this PowerPoint. So that we can kind of skip over that, but basically you can see these numbers. 376.26 is triple that of 125.42. And so any pyramid that has the same base and the same height, that means it's going to be 1/3 of the volume. And we can see all 3 of our formulas for volume here all in one place, where rectangular prisms are length, width, and height, and our triangular prisms are length, width, height, dividing it by 2 after that, and pyramids are the same thing, but dividing by 3. And that covers basically everything you need to know about prisms and pyramids as far as their volume formulas go. Now, just keep in mind that you might be given length, width, and height in problems, but you may and multiply them all together and then divide by whatever number that's appropriate. But you also might be given the volume and have to solve for one of these. So like for instance, you might know that the volume is 20 and then not know the length, and then be given that your width is 2 and then your height is 5, and then you might need to divide by 2 and divide by 5 and figure out that the length is also 2. So you might need to do a little bit of solving equations, but you shouldn't have too much trouble with that using some nice solving equation skills. The second part of this lesson is on cylinders, cones, and spheres, which are a little less familiar to most people than the prisms are. So to get into that, first we want to remember that circumference and area of circles that you've learned about in the past. Circumference for a circle is 2 pi r, and the area of a circle is pi r squared. In later parts of Math 3, we'll explore really where the circumference formula comes from and why pi is the way it is. So that's something to keep in mind for later this semester. And so when we're looking at circumference and area of using these formulas, depending on what kind of units you're given, you might need to adjust your circumference and area. So just remember, circumference is 2 dimensions because it's just the length all the way around, or technically it's 1 dimension actually. So it would just be inches or just centimeters, whatever it is. And then area is a 2-dimensional measurement. So that needs like centimeters squared or inches squared. So now if we try some of these examples, if our radius is 3, well, our circumference would be 2 pi times 3 or 6 pi. And so you can use your pi button on your calculator, or you can leave it as 6 pi, or you can make it into a decimal using 3.14. If you use the pi button on your calculator, you would get an answer of about 18.85 centimeters. The area would then be pi times 3 squared, or pi times 9. And 9 pi in your calculator equals 28.27 centimeters squared. For 6, that is 2 pi times 6. So that'd be 12 pi. And then you can put that in your calculator. And then pi times 6 squared would be 36 pi. You can put that in your calculator. So a lot of times, and we'll see later this semester, we're leaving the pi in there will be very helpful. But when you already have a decimal, you would usually just go right into the decimal version of your answer. So 2 pi times 4.5 ends up giving us an answer of 28.27, and that is centimeters. And then area 4.5 squared times pi would give us an answer of 63.62 centimeters squared. And that's just got a quick review of those circumference and area formulas there. So moving along, kind of similar to before, if we think about the volume of a rectangular prism compared to a cylinder. So before, we knew the area of this one square. We could find the area of the face and then multiply it by the depth. So when we talk about cylinders, you can find the area of the top or the bottom circle on a cylinder just using the area formula we already looked at in our last slide. And so if we knew the area of our circle on the top, well, we can multiply it by how tall it is, just like the cards earlier, and find out the volume of the entire cylinder. And that's kind of what we see here. It's a little hard to see right here, but these are supposed to be stacks of pennies. So if you knew the area of that one penny and you knew how many pennies you had, well, that would be able to tell you, well, how much volume is there in that particular stack of pennies. And that's the same idea as the cards earlier. The same idea we just discussed in our last slide as well. And that is how you handle the volume of any cylinder. And we're going to be looking at right cylinders, basically the ones where your top and bottom faces are directly above each other. We're not going to worry about kind of cylinders that are off kilter one way or the other or diagonal at all. But those do exist. So now, if we think about the relationship between a cone and a cylinder, they are very close in comparison as long as they have the radius and height that are the same. Radius of the face is what I mean, and then the height of the cone, height of the cylinder as well. It turns out that when you look closer at the relationship, that the cylinder and a cone, well, a cone is, there's three cones basically going into one cylinder, and that 1/3 right here would be the only difference you need to note for the cone formula for volume. And I found a video on YouTube that I have linked here in the PowerPoint that you can watch that kind of demonstrates filling up a cylinder and then kind of pouring it into a cone. And it's very obvious in that demonstration in the video that a cone is 1/3 of the volume, or can hold 1/3 of the capacity that a cylinder with the same radius and height could. And you notice that pi is in common as well in both. And lastly, you have a sphere as part of this. So the volume of a sphere is a pretty complicated formula, 4 pi r cubed over 3. And that is a formula that is not quite as easy to derive or create. And you need a little bit of kind of higher level math to really get where that comes from. And that's something you'll learn about in a future class once you've kind of acquired the extra skills you need. And that covers all of the basics for the volumes of different shapes. A lot of this may be review, but it is good to kind of go over this because we'll be using all of these volume formulas for some problem solving and adapting it to the real world. And that's going to be a big overarching theme of Chapter 4, Modeling with Geometry. And that concludes this first lesson of Chapter 4. Thank you for watching.